because I'm here today on a matter of great importance. Air! Air! The stuff that goes swish! Ha ha ha! Swish up chimneys! Swish down from the rotor blades of a helicopter! And sometimes swish around and around! In other words, air flows! Things that flow are called fluids. And since air flows, that makes it a fluid too. I want you to think about that while you look for answers to today's science questions. Question: what effect does the fluid called air have on a ball plowing through it? How do air currents flowing around an airplane wing help lift the plane into the air? What happens if a ball spins? Whatever method you use to find the answers, I think you'll find the study of aerodynamics very interesting. Very. Today it's up, up, and away!
The professor asked us what effect air currents had on the flight of a ball. Doesn't that imply that the effect would be different if it were something else? A piece of paper or a block of wood? I think the professor may be trying to get us to notice the effect of air currents on different shapes. I could do that on my own.
What I thought of when he was asking about spin was something I saw in a magazine about a new kind of golf ball that's not supposed to hook or slice. I wonder if the scientist who invented the new ball would answer a letter.
The science teacher sent me into the lab storeroom the other day. I saw a deal that I'll bet is used to find answers to questions like those the professor's asking. Do you suppose the teacher would let me experiment with some of his stuff?
Sure. When the professor said air was a fluid, I thought, then the way to get the answers is to look up stuff about things that flow. Fluids. Right. Wouldn't it just be as simple to ask someone? You could ask a pitcher who throws a curveball how he does it.
It's the spin that does it. The spin and the way the stitches and surface drag air around as the ball spins through the air. Well, now this is the way it was explained to me. Can I have my autograph back a sec? Now, the faster air moves, the lower its pressure. See? Now, I blew across the top there, and the air is moving faster, which means its pressure is less. Now, did you see how the paper was pushed up? Now, the underneath air has a greater pressure, so it pushes the paper up where the faster moving air is. You got that? All right. When I throw a straight ball, no spin, it moves in one direction, parting the air it meets, right?
Right. Like the air was going the other way from the ball.
Right. What you're picturing is the steady stream of air past a ball in flight. Streamlines. When I throw a ball with the top spin, I add something, because the stitches and the surface of the spinning ball drag some of the air molecules it hits into a spin too. Therefore, the air near the surface of the spinning ball is caused to swirl around in the same direction that the ball is spinning. Okay, let's put them together. The steady stream of air passing a ball because of its forward motion, and the air that is being dragged around by the surface of the spinning ball. To make it a whole lot simpler than it really is, if the ball has a top spin, the steady stream air and the swirling air are moving in opposite directions above the ball and moving in the same direction beneath the ball. This means the air is moving faster below the ball than above the ball. Now, we showed just a minute ago that the faster air moves, the
lower the pressure.
Right. So what's going to happen?
The ball is going to be pushed down. A drop ball.
Right. Now, a ball curves in the direction it's spinning. Ever notice what a pitcher does when a new ball is put into play?
He roughs it up,
Why would he want the surface to be rough?
so more air would be drug around it while it was spinning, so it'd curve more. Hey, that's the reason for the grip. With more seams out to catch air when you throw one of your spinner.
Right. But I've got to get back out on the field.
Sure. Thanks a lot. That answers the professor's question. If a ball spins, will it change direction? It sure will. Just look at it. But if that's so, then how come an airplane doesn't have to go into a spin when it changes direction? Must be a reason. I wonder what it is. Fluids, fluids, fluid flow. Here we go. To understand what happens when objects move through fluids such as air or liquids, we must observe streamlines. Fluids move in smooth paths of steady flow, or streamlines. The fluid flowing between two streamlines continues to be between them. If the streamlines crowd closer together, moving around an object, the same fluid still runs between them, like a river between its banks. Where the streamlines narrow, the fluids must move faster, because the same mass must now flow through less space in the same amount of time. For some reason, I keep thinking about that little plastic thing, the toy that used to be around here. Blowing was what made it work. Oh, here it is. Weird. As long as the air is moving, as long as I blow, air will hold the ball up. Now, why would it float on air just because the air is moving? I wonder if it has anything to do with the ball size or weight. Would the same thing happen if the ball were bigger? How could I find out? Hey, mister, can I use some of your air?
Sure. What pressure does your tires take?
Pressure?
Yeah.
Oh, it's not for my tires. I want to see if I can float a ball.
What? Come on. Okay, there you go. Well, son of a gun. What else can we do that with? Ooh. Do you suppose we have enough pressure to float this? Let's see. Oh, wow.
Pressure. Pressure. That's it. Only it's not pressure like inside a tire. What's happening here is because of the pressure of moving air. And what it looks like is, the faster the air, the less the pressure, and the more the lift. I suppose that's why big airplanes have to have long runways, so they can get up enough speed, make the air move fast enough over their wings to get the lift they need. Only airplane wings aren't shaped like a ball. Shape. Shape means something. Shape. Well, that's what happens to something flat. It flutters first this way, then that. This piece is exactly the same, except I'm going to change the shape. Made into a ball, it'll go through the air with hardly any wobble. No fluttering like the flat piece. Now let's see if I can make something kind of like an airplane. Look at its sail. Well, I may not have answers to everything the professor wanted to know, but I figured out that air pressure, speed, and shape are all a part of aerodynamics. Wonder what I missed.
Was that the mail, dear?
Yeah, but there's nothing for you. Just a letter for me.
For you?
Yeah, it's from one of the guys that wrote to you about this new kind of golf ball. These guys invented a golf ball that's not supposed to hook or slice. I asked them how did it work. Just something I've been fooling around with.
You wrote to some busy people just because you're curious?
Sure, why not? My associate, Dan Napella, and I appreciate your interest. I'll do my best to answer your questions. First, we began our experiments in an effort to help those golfers who have difficulty hitting a ball straight down the fairway. You see, a regulation golf ball must meet only 3 standards. One for weight, one for diameter, and one for the velocity it attains when subjected to a certain impact. Within such limits, manufacturers have come up with what they consider a good ball, one whose rubber surface is dimpled to provide aerodynamic lift and maximum distance. But if the ball isn't hit squarely, the club face imparts an unwanted spin, so that the dimples, instead of causing lift, cause a sideways thrust, the makings of a hook or slice. What we found when we eliminated some of the dimples by covering them with plastic kitchen wrap was that there is no need to orient the ball when it is teed because the ball corrects itself for you. What we found was that we had reduced the tendency to hook or slice. However, the first models reduced the potential distance the ball might travel, but further refinements resulted in a ball with normal distance, and it still resists hooking and slicing. It operates on a gyroscopic effect. Sincerely, Fred E. Holmstrom.
You forgot this.
What is it?
If you're going to investigate how air currents around a wing help lift a plane, you'd better find out. Suppose you take this straw and blow a stream of air between these 2 balls. What do you think will happen?
I think the pressure would push the balls. Probably away from me, but maybe just apart.
Try it.
Son of a gun.
I expect all of your friends have run into a variation of what you're seeing, if they dug far enough in trying to answer the professor's question, even though they might not have known what to call it. Bernoulli's Paradox.
Hey, wait till I spring that on the game. Bernoulli's Paradox.
Bernoulli's Paradox, meaning that at an intermediate flow speed, the pressure is less where the flow is faster. But now, what have you built here?
Well, I think I can show why a wing shape,
An airfoil?
why an airfoil works because of pressure differences between the upper and lower surfaces.
How do you plan to get air to flow over your airfoil?
By putting the airfoil out a car window.
Okay. How do you plan to measure the pressure above and below your airfoil?
Tube goes to a hole on top of the airfoil, and this tube goes to a hole on the bottom of the airfoil. By connecting either tube to the pressure gauge, I can measure the difference of pressure above or underneath the airfoil.
Okay, let's go try it.
Let's try it like that, with the bottom hole hooked up.
All right. Now I'm driving at 40 miles an hour. You can see there doesn't seem to be much change in the fluid. I'm going to speed up to 55 miles an hour, and let's see what happens to the fluid level. Okay, there doesn't seem to be much change at all in the level of the fluid, which means that the pressure underneath the wing stays about the same no matter what our speed is. Why don't we try hooking up to the top hole now? And I'll slow back down to 40 miles an hour again.
Wow, look how much lower the pressure is.
Now let's try and speed up to 55 miles an hour and see if that makes a difference.
It's much higher than it was before.
And as we go faster, it decreases the pressure even more on the top of the wing, which allows the wing to lift up. Okay, Sylvia, try holding the airfoil outside the van now with your hands to see if you can actually feel the lift.
It's been pushed up into the lower pressure space. This means that the air has to speed up to get over the top edge of the airfoil if it's good.
You're right, but tell me, how do you know?
Because of what Mr. Bernoulli found out. Otherwise, the airfoil wouldn't rise unless the air was going faster.
Well, does that answer all your questions?
All the ones I started with, but now I have new ones. Now I wonder how that funny-shaped wing I saw on the military jet at the air show works. Do these rules stay the same when something's traveling at jet speed? I wonder.
I learned that the faster the air flows, the less the pressure.
Bernoulli's paradox.
And the lower the pressure, the greater the lift, provided the lower pressure is on top of the airfoil.
Bernoulli's paradox.
It's spin and the surface that make a curveball. Yeah, we know. Bernoulli's paradox. Boy, when you learn something new. Pipe down. It's time for the professor.
Swish! Swish! Oh, swish! Ha-ha! Have you learned all about how airplanes, curveballs, and gliders function in that marvelous fluid, air? If so, I bet you're ready to apply what you know to a whole new set of questions. How about this one? How does a sailboat move against the wind? Why does a spot of grease on one side of a spinning ball make it wobble? Or what about this one? Why does a spinning table tennis ball sometimes curve the wrong way? And here's a good one. What properties affect the flight of a hang glider? Well, those questions ought to keep you up on the air for a while. But remember, you can choose your own technique for finding the answers. You can read about whatever you need to know to come up with an answer. You can experiment. You can ask questions. Or you can simply observe how things work and think it through. Whatever method you use, I think you'll find it's fun to wonder, but it's more fun to know. Been nice talking to you, but it's time for me